We've talked about generating confidence intervals and performing hypothesis tests about the difference in two population means. So far, we've assumed that those two populations are independent of each other. That is, we collect a sample from population 1, we collect a sample from population 2, and those two samples, as well as those two populations, don't affect each other. For example, if we collect samples of maple and samples of oak lumber, and we perform strength tests on each, the strength measurements of maple don't affect the strength measurements of oak, and vice versa. The strengths of maple lumber are independent of the strengths of oak lumber, and we make our comparison of these strengths of these two populations with the assumption of independence. But there are certain situations where the independence assumption fails. This is best illustrated with a few examples. We might want to determine if a training course improves the productivity of operators that work on a factory floor. Now, we could collect a sample of operators who have had the training and measure their productivity, and we could collect a sample of operators who haven't had the training and measure their productivity. Then we could compare their means of productivity with the techniques that we've already talked about. But that's not the most effective way to address the specific effect of the training course. The best way would be to measure the productivity of a sample of operators who haven't had the course, then let them sit through the course, and then measure their productivity afterward. We could compare their productivity before and after the course, considering those to be two populations, the before population and the after population. And we could answer hypotheses about how different those two populations are. But those two populations contain the same individuals. The operators are in both the before training and after training populations. The populations are not independent of each other. As another example, we might ask the question, did a change in tire brand impact the fuel economy of taxis? We collect a sample of taxis with one brand of tire and a sample with another brand of tire, calculate the fuel economy of each, then make a comparison. And if we only have data describing those two populations separately, then we have to assume independence and use techniques that require the independence assumption. However, if we're designing this experiment from scratch, we could measure the fuel economy of a sample of taxis whose tires are of a specified brand, then change the tires on that sample and measure the resulting fuel economy after the change. That would get directly at the effect of tire brand on fuel economy. With both of these examples, the two populations that we're interested in are before and after. Before some change, we take a sample, measure something about that sample, then we make the change and measure the same sample. In such a case, we have to intentionally design an experiment such that the independence assumption fails. We have to recognize in advance the best way to answer our hypothesis is a before and after kind of experiment where the sample is in both populations. We call this situation a paired sample or a matched sample. As we said, each observation belongs to both populations. How we analyze the data for each observation is by taking the difference in outcomes for each observation. Let's take a look at an example. Say we have a number of observations n, and each of those n observations belong to both population 1 and population 2. For each observation, we take the population 1 measure and subtract from it the population 2 measure. In our example, for observation 1, the measure taken from population 1 is 14, and from population 2 is 7. So the difference is 7. For the second observation, the difference between population 1 and population 2 is 13 minus 9, or 4. We find this difference d sub I for all n observations. Then we take the sample mean and sample standard deviation of the differences. That is, for the mean d bar, just like we've always done, we sum up the differences and divide by n. For the standard deviation, we take each difference and subtract the mean of differences d bar, square it, sum it over all n observations, then divide by n minus 1. And so, d bar and s sub d are our point estimates for the mean paired difference and standard deviation of paired differences for the populations. The actual mean paired difference is denoted as mu sub d, and the standard deviation of paired differences is sigma sub d. We might be interested in estimating mu sub d with d bar. Of course, we know that we can do better than a point estimate. Let's look to formulate a confidence interval as the point estimate, d bar plus and minus a margin of error. And that margin of error, as we well know, is a function of variability, sample size, and confidence. Our 1 minus alpha times 100% confidence interval is pretty straightforward. It's d bar plus and minus t for our particular degrees of freedom, with alpha over 2 in each tail, multiplied by s sub d over the square root of n. We're 1 minus alpha times 100% confident that mu sub d, the true mean paired difference, is inside the bound somewhere. The degrees of freedom is calculated with n minus 1. Let's take a look at an example. Say that we're assembling components into a larger radar assembly. We have a standard approach to assembling these radars, and we want to experiment on a new assembly approach that might eliminate some unnecessary movements and ultimately reduce assembly time. We collect a sample of 12 operators, and we measure how long assembly takes using the standard approach. Then we measure how long it takes for the new approach. When we treat this as a paired sample, we account for individual performance using the two approaches. For example, some operators may be a little quicker than others naturally. We account for that with the paired sample. With operator 1, the assembly time with the current approach is 63.3 seconds. And with the new approach, it was 57.8 seconds, for a difference of 5.5 seconds. We find the difference calculation for all 12 operators. The sample mean paired difference, d bar, is 4.83 seconds, and the standard deviation is 1.76 seconds. And so we want a 95% confidence interval for the true mean paired difference. Our measure of confidence, the t-value with 0.025 in each tail, is calculated for n-1 or 11 degrees of freedom. If we go down to the row in the t-table for 11 degrees of freedom and over to the column associated with 0.025 in the tail, we get a t-value of 2.201. So our confidence interval is calculated as 4.83 plus and minus 2.201 times 1.76 divided by the square root of 12. The bounds on the confidence interval are 3.71 seconds and 5.95 seconds. That suggests that we're 95% confident that the true mean paired difference between the current standard assembly approach and the new approach is between 3.71 and 5.95 seconds. Note what it means to have two positive bounds. It says that the current approach minus the new approach leads to a positive number. That means the current approach must be larger, it must take more time. So we're 95% confident that the current approach takes longer than the new approach by somewhere between 3.71 and 5.95 seconds. We can also form hypotheses about the mean paired difference. For example, we might want to know if the actual mean paired difference, mu sub d, is d naught, or something other than d naught. In such a case, we might have mu sub d equal to d naught in the null hypothesis, as equality is always in the null, and the contradictory statement, mu sub d not equal to d naught, in the alternative hypothesis. That is the mean paired difference equal to some value, or is it not? And as always, we have two other options for framing our hypotheses. Greater than or equal to in the null, with less than in the alternative, or less than or equal to in the null, and greater than in the alternative. The test statistic has a similar look to what you'd expect. It's a t-test statistic that measures the difference between the sample evidence, d bar, and the hypothesized value, d naught, in standard deviation units, s sub d over root n. And we could use the critical value or p-value approaches the same way that we've always used them. Let's look back to our assembly time example. Say we want to know whether the mean difference, current standard minus new approach, is more than 4 seconds. More than 4 seconds implies strictly greater than. Since that's not an equality statement, greater than must be in the alternative hypothesis. Therefore, the contradictory statement that includes equality must be in the null hypothesis, mu sub d less than or equal to 4 seconds. Recall that d bar from our example is 4.83 seconds, and the standard deviation of the sample paired differences is 1.76 seconds. Implementing the test statistic, we get a t naught of 1.63. If we check out the t-table, we find that for 11 degrees of freedom, a value of 1.363 on the t-axis is associated with 0.1 in the tail, and a value of 1.796 on the axis is associated with 0.05 in the tail. Our test statistic of 1.63 is found in between these two values. That suggests that the p-value is between 0.05 and 0.1. Depending on how much confidence we want to have in the result, that might be compelling enough for us to reject the null hypothesis and conclude that the mean paired difference is indeed greater than 4 seconds. If we use the t-dist function in Excel, we find the p-value to be more exactly 0.066. Note that those without a course in statistics might say, well heck, the sample mean of 4.83 is obviously more than 4 seconds, so we reject the null. But we know better than that. We know that we have to be compelled by the sample evidence when we account for variability in sample size, and we want to have some amount of confidence in the result. We can't just take a point estimate and draw a conclusion. We need to use the methods of inferential statistics. And in this case, the decision is fairly close. A p-value of 0.066 is only somewhat compelling. And so this concludes our discussion of paired or matched samples. where the two populations, whose means we're interested in studying the differences of, are not independent. We see the need for a paired sample test arise often in before and after studies, though any situation where the same observations make up both samples would require a paired sample approach.